Simple harmonic motion. Notes. Simple harmonic motion is an object oscillating up and down or back and forth about an equilibrium point. There's a restoring force that pulls it back to the equilibrium point, and then it passes and the restoring force pulls it back again. So it oscillates back and forth, having a regular pattern or a cycle. When the spring is at its maximum height, the restoring force is gravity pulling it back down. When the spring is at the bottom, the restoring force is the force of the spring pulling it back up. And it's due to the restoring force always being proportional to the displacement that makes it oscillate back and forth. Amplitude is the term for maximum displacement. In the formulas, we use x for the displacement. We don't use amplitude. Frequency is given the symbol small f. Large F is force, so you have to be careful of your cases. Frequency is the number of cycles in 1 second, cycles per second. It's measured in the units of hertz. Hertz means per second. So if we have a frequency of 5 hertz, that means it's oscillating 5 times per second. Periods given the symbol capital T, and that's the time it takes to complete one cycle. We're going to call it the number of seconds per cycle. Putting the definitions this way, we can see frequency, cycles per second, and period is seconds per cycle. They are inverses of each other. We can also use these definitions to calculate what is the period and what is the frequency by dividing the number of seconds and the number of cycles. This is the period formula for an oscillating spring. Period is 2 pi times the square root of m over k. So you can see if I add more masses to the spring, we're going to increase the period. If I increase k by getting a stiffer spring, I'm going to decrease the period. Here's a spring with a low spring constant. You can see it's moving fairly slowly. Looking at the equation, if we have a small k, if you're dividing by a small number, you're going to have a large period. A large period means that it's moving slowly. It takes a long time for it to complete one complete cycle. Here's a spring with a high spring constant. You can see it's moving fairly rapidly. So if we have a large k, that means we're dividing by a large number. You're going to have a small period. Small period means it's moving fast. It has to complete one complete cycle in a small period of time. Pendulums also have harmonic motion. This is the equation for a period of a pendulum, very similar to the period of an oscillating spring, 2 pi times the square root of L over G, where L is the length of the string. Again, we have a repeated pattern back and forth. We can see the angles the same on both sides, the height's the same on both sides, and the time is the same on both sides. When the bob is on the left side, the restoring force is towards the right. Gravity is trying to pull it back down towards the equilibrium position. When the displacement is on the right, the restoring force is to the left. The restoring force is always opposite the displacement. Hooke's law is a relationship showing the force of the stretched spring, the spring constant, and the displacement. Up until now, all the forces we've looked at have been constant forces. The force of gravity, a normal force, a tension force, an applied force, and force of friction are all constant forces. The elastic force is not constant. It changes with how far the spring is stretched. Now, relating this to Newton's second law, if our force is not constant, then our acceleration is not constant. The acceleration depends on the force, and the force depends on the distance that the spring is stretched. So we'll write it like this. We'll say the acceleration is proportional to the force, which is proportional to the stretch. This is what Hooke's law is showing. This is a spring with a hanger hand on it, and this would be our equilibrium position. And when I add a mass to it, it's going to stretch a certain distance. So the equation is F equals k times x. We can predict how far it stretches if we know the spring constant and the force of gravity acting on it. If I add the same mass to it, it will stretch the same distance one more time. This is what Hooke's law is telling us, that this distance is proportional to the mass. So if I double the mass, I'm doubling the distance. Looking at an example here, they're going to ask you to explain where is the force at a maximum, where is the force at a minimum, where is the acceleration at a maximum, where is the acceleration at a minimum, where is the speed at a maximum, and where is the speed at a minimum. So if we'll stop at the top here, this is my maximum displacement, so x is a maximum, and I know F equals k times x, so the force has to be at a maximum when it's at its extremes. If the force is at a maximum, then the acceleration is a maximum because F equals m times a. So at the very top and at the very bottom, we have maximum x, maximum force, and maximum acceleration. When the object's in the center, when we're at our equilibrium position, equilibrium means the forces are in balance, the spring and gravity are balanced with each other, so there's no net force acting on it, and that means there's zero acceleration in the center. If we look at the object as it's oscillating, we can see it's going faster in the center and slower at the edges. In fact, it stops at the edge because it's turning around and going the other way. So I'll explain that this way with the conservation of energy. This is the formula for the energy stored in a stretched spring. 1/2 kx squared is the potential energy stored in the spring. As it's oscillating back and forth, that potential energy changes into kinetic energy. So at the equilibrium position, your x is 0. That means you have no potential energy, so it is all kinetic energy at that point. So at the equilibrium position, you have your maximum kinetic energy, which is where your maximum speed is going to be. Looking at the graph, displacement versus time, as the object oscillates up and down, we're going to get a sine wave graph. The object is oscillating above and below the equilibrium position here. The highest displacement is called the amplitude. And one complete cycle is going to go up above and down below once. So this distance is one complete cycle. And being that this is a time graph, that distance is representing the period. If you get a graph like this on the AP test, they'll give you something like a time down here and ask you to find the period and frequency from the graph. You can see there's 2 complete cycles. So if 2 complete cycles is 4 seconds and 1 complete cycle is going to be 2 seconds. If we know the period, then the period is the inverse of the frequency, so we can do 1 divided by 2 to get 0.5. The other way to calculate this is using the definitions I gave you. Frequency is cycles per second, so I can do the 2 divided by 4 to get the frequency. And period is seconds per cycle. I can do the 4 divided by the 2 to get the period. The last equation we're going to do is the displacement, which is the complete distance that the object travels. As it's oscillating up and down, what is the complete distance that it goes? Or it's the distance along the path of the sine wave. So this is equation for this. Usually we use sine, but sometimes they do cosine. It's the same shape. The distance along the path is the amplitude multiplied by the sine of the angular speed multiplied by the time. Now we know speed times time is distance, and from the equations we did last week, the angular speed times the time is the angular distance, or the theta. So this is just a times sine of theta. We also had the equation last week relating the angular speed with the frequency. We can combine that with, we know frequency is 1 over the period, and we can combine that with the period formula to come out with this relationship that shows the angular speed is the square root of k over m. End of notes.